Networking is done with TCP-IP. This is the same network technology used to construct the Internet. The same underlying protocol is used to construct email, FTP, the File Transfer Protocol, and HTTP, the Hypertext Transfer Protocol, and several others. In the next lesson, I'll be showing you how these are all set up in Linux, but right now I need to go over some of the fundamentals. The word Internet has two different meanings. When you're referring to that huge network that covers the globe, it's generally capitalized like this. That's what's known as the Internet. When you refer to the technology itself, the protocols and whatnot, it's spelled with a lowercase I like this. This is an Internet, as in the two computers were communicating using an Internet. I know you can't see the spelling when I say it, but right now I'm talking about the technology and I'm explaining the fundamentals of the Internet with a lowercase I. Any computer connected to an Internet is called a host. It doesn't matter whether it's a server or a client or a router or whatever, every computer is called a host. Every host has a name. The name of the host on which this is being recorded is retro. Linux computers on this same local network are named Arlen, Alice, and Cygnus. You can name your host just about anything you like, as long as no other host on the same Internet has the same name. Every host has an IP address. Now this is a 32-bit number that uniquely identifies the host, just as uniquely as does the host name. For example, the IP address of this host is the 32-bit number shown here. This same value can be written as a hexadecimal number this way. But the most common way to represent an IP address is to write the value of each of the 4 bytes of the number as a base 10 number and separate the 4 numbers with periods, like this. All 3 of these are the same address, just written differently. The reason for writing it in this format is that this format makes it more convenient to categorize addresses for subnetworks and network types. For example, any address such as this one that has the first 2 bytes of 192 and 168 is for local network only. If you are setting up your own local network of 2 or more computers, you should use this address scheme because things sent to this kind of address will be restricted to your local network. It will never be sent out over the Internet at large. That is, your 192, 168 addresses won't mix up with my 192, 168 addresses, even if we both happen to be connected to the Internet at large at the same time. But this is not all of the address you'll need. You need one more number. The IP address will get the message to the correct host, but you also need a port number to target a specific application on that host. This is just a 16-bit number that identifies which application is to receive the message. For example, if you have a web server running on your machine, web browsers know to include the port number 80 in the message that they send to it. The web browser is sitting there waiting for any message that comes into that host and addresses port number 80. An email server would have a different port number. FTP has another port number, and so on. This way, a single computer can simultaneously be a host for several different services. All messages sent to a host include the return IP address and port number, so the host will know how to respond. When one host initiates a conversation, such as when you dial up your Internet and send a message to a mail handler, your computer already knows that that port number is 25 because that is the standard number. These standard numbers, and there are lots of them, are called the well-known numbers. And one other thing, the message sent has to be formatted into the correct protocol. This protocol thing is a bit complicated and can get very baroque, but there's no need for us to go into that sort of thing here. All you really need to know now is that there are protocols and that these protocols define the exact layout of the message. You're probably familiar with the email protocol, which is SMTP, which is an acronym for Simple Mail Transfer Protocol, and you've seen HTTP, which is Hypertext Transfer Protocol, and you've come across FTP, which is the File Transfer Protocol, and there are lots of others. There are two fundamental ways to send messages. When a process on a host wishes to establish a two-way connection and have a conversation with a process on a remote host, the sent and received messages are encapsulated in TCP packets. TCP stands for Transfer Control Protocol. The sender receives verification that the message has been received. If it's a large message, it may be broken into pieces, and each piece is acknowledged by the recipient. Error corrections will take place if necessary, including resending parts of the message as necessary. A simple example of an application that uses TCP is FTP. A file being transferred is broken into packets, and each packet is sent individually, and any packet that doesn't make it intact can be resent. I'm simplifying things a bit here, but that's the gist of it. Another way of sending messages is UDP. UDP stands for User Datagram Protocol. This protocol also acts as a wrapper for whatever message you're sending, but the sender doesn't expect a response. The message is securely sent, that is, each host that transfers the message along its path to its target verifies that the message has been transferred correctly, but the original sending process is not notified and must simply assume that the message made it. An example of a UDP message is email. The message goes out, but the sender doesn't receive verification of its receipt. In fact, an email message may linger around in the system for days before it finally reaches its recipient. So you can see the real name should be TCP-UDP-IP. In the next lesson, I'll be showing you how your Linux system can be configured to do all this stuff. This lesson is an introduction to the TCP-IP port numbers. Like other system facilities, the configuration files for networking are to be found in the etc directory. However, with networking being such a fundamental part of the Linux system, you'll find that it also exists in the form of numerous application programs and daemons, as well as the configuration settings. Let's start with the basics, the port number. A Linux system can be a server for any number of network facilities. It can be an email server, a web server, file server, and lots of other things. And it can be several of these things all at once. To do this, to be any kind of server, as we saw in the previous lesson, Linux must have a daemon waiting on the appropriate well-known port number. These numbers are found in the configuration file named etc services. Now, these numbers are assigned by the IANA, which is an acronym for the Internet Assigned Numbers Authority. As you can see from the comments here at the top of the file, the well-known numbers are from 0 to 1023. The registered ports are from 1024 to 49151. The registered port numbers can be requested and are assigned for special projects. It can be something experimental or a commercial product that needs to communicate over the Internet and for some reason needs to use its own protocol. The numbers from 49,152 on up are the numbers that can be dynamically assigned. These are used by local programs that don't have or need a well-known number. For example, if you start your web browser running and have sent out a request for a web page, it will also send out one of the dynamic numbers as part of its return address. Then it listens over that port for the response. This is why you can have several web browsers all running at once, each one of them waiting for data to come in from a different port. Again, I'm simplifying things a bit, but you should get the general idea. It was originally envisioned that there would be a separate set of port numbers for TCP/IP and for UDP. However, things evolved so that most often the same port number is assigned for both. While that's true for most cases, it isn't true in every case, so the format of this table allows separate port assignments for each protocol. The first column is the name of the service. You can see the simple echo server is on port 7. All it does is bounce back any messages sent to it. Port 9 is discard. Any messages sent to port 9 are simply read and ignored. Port 13 responds with the date and time, and port 17 will respond with a quote of the day. Of course, none of these will respond or act correctly unless a daemon is running and listening to that port. Notice that FTP has two port numbers, 20 and 21. It actually uses both of them to transfer files. It uses port 21 to converse back and forth, while port 20 is constantly feeding blocks of data. This way, it can maximize the throughput of data on one port while using the other port to verify the correctness of the transmissions. It doesn't have to wait for confirmation before sending another block, and the blocks can be sent in any order. Say, for example, a file is being transmitted in 20 blocks. FTP just starts sending them, one after the other, without waiting. But the receiving end finds that it has a problem with, say, block 7. It can request that block 7 be sent again, even if the transmission has moved on to block 9 or 10. It's quite fast and quite accurate this way. Here you can see that the email server, Simple Mail Transfer Protocol, is on port 25. Port 70 is the Gopher. Just a few years ago, Gopher was one of the main research tools on the Internet. You could access thousands of documents at hundreds of document repositories around the world. It worked fine, but it wasn't capable of presenting graphics. A new upstart protocol named HTTP appeared on port 80. It added pictures and fancy fonts and all sorts of things. It has completely replaced the Gopher system, which now is a tiny fraction of what it once was. In fact, HTTP has become so popular that many people think the terms World Wide Web and Internet mean the same thing. Here are ports 109 and 110. These are the post office email server protocols. I suppose we'll continue to have a new email protocol every few years. People always like to try new things with email. Here's the IRC port number, 194. As you can see, there are lots and lots of assigned port numbers. Some of them are used a lot, some of them hardly at all. There's just no way to tell, actually, what's going to be a hit. Here's port 443, HTTPS, the secure version of HTTP. Modern web browsers can connect to sites using this protocol to make secure connections. Here are some protocols that are specific to the Unix operating system. The exec protocol is for remote execution of programs. BIF is used to check for mail having arrived on a remote system. Most things in the Unix world are named using descriptive words or an acronym, but not everything. Once upon a time, a programmer had a dog that would bark whenever the postman would drop mail through the slot in the front door of his house. So when the programmer wrote a utility that would report on the arrival of mail, he named it after his dog. That's why UDP port number 512 is named BIF. This lesson explains more about some of the fundamental network configuration. We'll take a quick look into another file with well-known numbers and then look into the table of local addresses. In the previous lesson, I described the fundamental protocols named TCP and UDP as the two protocols used to encapsulate message packets transmitted over the Internet. While it's true that these two are used in most cases, there are others, and these protocols are identified by having an ID number assigned to them. These numbers are all listed in the file named protocols. Each listing in the file is made up of 3 fields. The first one is the name of the protocol, the second is the protocol number, and the third lists any alias names for that protocol. Notice that the first one in the list, the protocol number 0, is the IP protocol. Now this one is sort of a pseudo protocol because it consists of nothing more than the 32-bit number that identifies the host on the network. The ones you'll recognize are number 6, the TCP protocol, and number 17, the UDP protocol. You probably haven't heard of any of the others. There are protocols here that the Internet hosts use to talk to one another to tune and monitor the network. The version of the protocol used for the existing Internet is IP version 4, which is the 4-byte IP address. Someday, this 32-bit address size is going to run out, and plans are being made for the future in the form of an IP version number 6. Protocol number 41 is the new version with a much larger IP address, along with lots of other fancy new features. Each address will even include some notion of the geographic location of the host. As you can see, there are lots of protocols, but just about everything you do will either be TCP or UDP. Whenever an application wants to send something from one computer to another, it constructs the message, wraps it in the appropriate protocols, sends the message to the IP address of the target host. So its first job is to determine the address of the target host. The locally known addresses are listed in a file called hosts. This same file exists on all of the hosts of the local network, so they all know how to talk to one another. Notice the first address in the list, the one named localhost. This 127 address is another of those special addresses. When a message is sent to this address, it comes right back to a daemon waiting on a port on the local computer. This address will never transmit a message to another computer. The address of all the local computers is included in this list. The name of each of the local computers is also listed, and you can list more than one name for each one. The first name in the list is considered the host name, and the other names are aliases. The primary purpose of this table is to translate a host name to an IP address. On a local network like this, you can use any name you want for an alias. But if you use an alias that is the same as the name of a remote host, one that's not on the local network, none of your applications will be able to find that remote host. Whenever a program has a host name and wishes to find the address of that host, it looks here first. And you can put anything you like in here. For example, as the very last entry in this table, I have the address of the forums site for VTC. This means that when my web browser needs to go to that site, it doesn't have to send a request out over the internet to get the address. Now, this has the disadvantage that if the IP address of the forum's website were to change, I wouldn't be able to find it until I remove or change this entry. I am aware that there are ways to automate the construction and update of the host's file, but for now I'm just trying to cover the fundamentals. This lesson tracks a procedure taken by an application to send a packet over the internet. Given the name of a host, such as the kind of thing you would enter as a URL in a web browser, the application queries for the host name. This query first looks in the host's file. If it isn't found there, the search request is forwarded to a domain name server. Passing a request to a domain name server can cause a series of events to take place, and I'll be going over them in an upcoming lesson. For now, let's just follow the routing of a message once the address has been determined. A message may or may not be able to go directly to its destination host from here. The only thing that can be done at this point is to forward the message to some place so it will be closer to its destination than it is now. The routing table is used to determine the target host of this first hop. The target's address in the message is checked against the listings in the routing table to figure out which way to go to get to the next host. Here is the routing for this computer as it looks while this computer is dialed up and connected to the internet. Now let's start with the second member of the table. This is the general address of the local network. Notice that the first three numbers of the listed address are 192.168.0. Also, notice here the mask setting for this address. This mask value is ANDed with the address found here in the table. It's also ANDed with the target address, and if the results are the same, it's a match. That is, if the first three bytes of the target address are 192, 168, and 0, the message is sent to this local Ethernet. The name ETH0 is the name of the Ethernet device to be used. If more than one Ethernet card were in the computer, parts of the address space of the local network would be directed to ETH1 and ETH2 and so on. Anyway, the local routing question for the message has been answered, and the message is put on the Ethernet. In similar fashion, The address is checked against the next entry. That is, if the address begins with 127, it's considered to be a local message. And a local message is passed to the process waiting on the appropriate port, just as if the message had come from the outside. Now this bottom line is the default. If the target host address hasn't matched anything else in the table, it'll match the default. But the default is a gateway. All addresses that don't match anything else are tested against the gateway. And here is the gateway entry in the table. Now this gateway will accept any address. The message is then sent to something called PPP0. This is an acronym for Point-to-Point Protocol and is the name of the daemon that handles the dial-up connection to the Internet. This message is sent out over the dial-up link, and the host on the other end of that phone line is the one that will be able to handle it from there. I'll be explaining the PPP protocol and modems a little bit later. As for the Ethernet, the kernel keeps an internal table that holds the Ethernet information. The little utility named ARP lists the contents of this table. Ethernet cards come with an address already built into them. That is, every Ethernet card in the world has its own unique address, so it's just a matter of plugging them together to start communications. The address of an Ethernet card is 10 bytes long, and this provides enough address space to plate the entire surface of the planet with Ethernet cards. The Address Resolution Protocol, ARP, is used by the kernel to query the Ethernet and determines the addresses of any cards it finds. This protocol allows the kernel to match up host names with their Ethernet addresses. To show you the routing in action, there is a little utility named ping. All ping does is send an "Are you alive?" message to a host and measure the time it takes to get a response. In this example, I am pinging another computer on the local network. That is, the ping utility retrieved the address of Alice from the host file and used it to create and transmit a message. The router figured out that the address was on the local network, so it sent the message over the Ethernet. Alice got the message and responded. The message came back to the original ping utility and printed the size of the message on the screen, the amount of time it took, and the IP address of the remote host. And then ping did it again, and again, and again. Control-C breaks out of it. Ping can be used on hosts out on the Internet just as well. For example, notice that because this is a dial-up link, it takes a bit more time between pings. Also notice the name change on the returned ping. That's because both of these host names use the same host computer and the same IP address, but the real host name is belugalake.com. Now look at the difference here. I have a quick script I use to hang up my modem. The modem has been disconnected, so let's take a look at the route table now. Now these two entries that you see here are the ones that I configured into the routing table when I installed the system. The other entry is automatically added and removed when an internet connection is made or broken. If I try to ping anything outside the local network now, this is what I get. This lesson is about the domain name service of the Internet. Any host on the Internet can be uniquely identified by its domain name. There are only a few of these domains, net, org, edu, and so on, and every host on the Internet has an address registered with one of these domains. If you need to determine the address of some host and you know its name, you can find that address at the domain host. For example, to find the address of yahoo.com, the domain name server named com has that address. But you normally don't go directly to the domain host itself. If everyone did that, the traffic would be overwhelming. Your computer is connected to the Internet. It uses the name of the host computer to issue a request to a domain name server. Now, your internet service provider should give you the IP address of its domain name server. It's usually referred to as the DNS server. This host has a name, but you can't use its name because you have no way of looking it up unless you already have its address. The request that you generate is sent to the DNS server. If it has the address, it returns it to you, and that's the end of the transaction. It may have the address because the DNS server handles lots of clients. If someone else has requested that address recently, it may still have a copy. I say recently because domain name servers only keep the addresses in their files for a limited amount of time because the internet is always changing. The address could possibly become invalid after a short period of time, so after the information has aged for a while, it's deleted. Now, if this server doesn't have the address, it needs to go to a higher authority to look for it. This could be another DNS server, one that's further up the chain and is meant to handle requests from other DNS servers. There's no practical limit to the number of servers that can be in this chain. It just depends on the density of the internet. New servers are being constantly added to the internet to spread the load. As the request travels further up the chain, the more likely it is to find a DNS server that already has the address left over from some fulfillment of a previous request. But finally, at some point, if nobody has the address, the request reaches the ultimate authority, the domain host itself. This is where a complete directory of all addresses in the domain is kept. It acts like one computer, but in reality, for both safety and efficiency, it's several computers, and the request may go to any one of them. But it is the ultimate authority. It has all of the addresses in a large registry. When someone buys a domain name, it's only necessary to include the name in the tables on this one machine. Because of the way the domain name system handles address resolution, a new address is effectively distributed everywhere at the moment it's registered. The response then retraces the steps it took to get here. Along the way, each of the intermediate DNS servers makes a copy of the address for its files, so it will have it in case someone asks for it again. The response eventually returns to your computer, so your browser can now send out the request for that web page or whatever it was after in the first place. Well, that's about all I'm going to do with the internet. This course is about Linux, so I'm going to get back inside that box. The next lesson is about a facility that Linux uses to reduce the number of daemons that are waiting on a port. This lesson is about xinetd, the super server that manages the other servers. As you could see by looking through the list in the services file, for your computer to supply these services in the normal way, you'd have to have lots of sleeping daemons on your system. Well, xinetd takes care of that for you. Let's take a look at the list of scripts that start daemons running. Notice that the next to last script in the list is xinetd. The script has the same name as the daemon it runs. You can see here that the daemon has a process ID number of 675, which indicates that it started running shortly after Linux was booted. It listens on several different ports, the port for any of the internet services that you wish to run. When a message arrives on one of those ports, xinetd starts the server to let it handle the message. While the server is handling the port, xinetd stays out of the way. The service proceeds normally. When the service finishes doing whatever it does, it quits running. Because the service was run as a child process of xinetd, the xinetd daemon is notified, so it goes back to listening on the port. Some of the services work a little differently. Some services require a separate server for each request. In this case, xinetd will respond to the port by starting the service running, but continue to listen to the port. When a new request comes in, a new server is started to handle it. xinetd manages a number of services, so it's called a super server. The original version of xinetd was inetd, and it still has that name on some Unix systems. The name inetd is sort of an acronym for Internet Daemon. The new name, xinetd, is sort of an acronym for Extended Internet Daemon. The software to handle the services is normally installed as part of Linux. Some of them will require some configuration, but to enable and disable services, it's primarily a matter of modifying the configuration files for xinetd. When xinetd starts running, it gets its settings from the configuration file in the etc directory named xinetd.conf. The values shown here as defaults inside the braces are the default value settings used for all services. Notice the include command toward the bottom of the file. That is the name of the directory that contains the settings for each of the individual services. There is one file here per service. To adjust the settings for any service, you need only adjust the contents of the individual file. For example, this is the file that configures the telnet service. I don't want to try to go through all the options. There are lots of them, and they can be complicated, and you wouldn't remember them anyway. And they're all described on the man page named xinetd.conf. In this example, with wait set to no, xinetd will not wait for the telnet server to finish. Instead, it will start the server, then go back to listening to the port for any other requests. The server program itself is named in.telnetd and is in the user sbin directory. Disabled is set to yes, which means the service is disabled. This is the configuration file for the finger service. This is a very old service that originated with a BSD Unix system. It allows a user on a remote computer to query this computer for certain user information. As you can see, it is also disabled. Let me show you the steps required to enable this service. It's necessary to switch it from disabled to enabled, then save the file. But there's one more step. Even though the configuration has been changed, the daemon xinetd has not been notified. Different versions of Linux provide different utilities to notify a service of a configuration change, but they all come down to doing the same thing. If you restart the server, the one that's running is halted and a new one is started. When the new one starts, it reads all the configuration files and gets the changes. The finger service is now enabled. And as you can see, we now have a new process number for xinetd. This lesson is an introduction to NFS. NFS is the Network File System. It allows you to mount directories on remote computers to directories on your local machine, just as if they were local disk drives. We looked at NFS a bit earlier when we looked into the file system configurations, and NFS daemon acts as both a device driver and an internet service. This lesson describes NFS as sort of an introduction, but it doesn't go through all the steps necessary to implement NFS on your system. For that, I'll refer you to the web page again, where you'll find a link to the NFS how-to. It's much better than anything I could come up with. In fact, NFS configuration is not something I do a lot, and this how-to is the one that I use to configure my system. Anyway, let me explain how this stuff works. There is a Linux facility called RPC, Remote Procedure Call. A programmer can write a procedure or a function or whatever you want to call it and set it up so it can be called remotely from another computer. When a program wants to have one of its procedures published so it becomes available on the Internet, it's registered with a daemon known as the port mapper. The procedure itself has an ID, and the port mapper associates an Internet port number with that procedure. A remote caller first requests the port number of the procedure, then it can use that port number to remotely call the procedure. The utility program named RPC Info queries a remote port map daemon to get a list of the procedures, like this. The first two columns contain the ID and version of the remote procedure. The next two columns specify the protocol and the port number associated with that procedure. On the right is the name of the program. In particular, notice that there are a couple of NFS procedures along with a lock manager and the mount daemon that's used to mount the remote file systems. An NFS server is a computer that allows one or more of its disk drives to be mounted by a remote system. That is, it serves its disk space to other computers. A client is a computer that mounts one or more remote disk drives as local drives. It's common to configure a computer as both an NFS server and a client. That way, computers can reciprocally share their disk drives. But this diagram just shows the daemons that must be running for a server and the daemons that must be running for a client. On the server, RPC NFSD does most of the actual work. The daemon pair RPC LockD and RPC StatD keep track of the general status of transactions and handle all the file locking. The daemon RPC MountD handles all the remote requests that come from the remote computers. The daemon RPC RQuoteD handles the quota limits imposed on the file systems when they're mounted remotely. The port map daemon is required, as described earlier, to convert RPC function ID numbers into port numbers. Things are simpler on the client side. The RPC StatD and RPC LockD generally manage availability and keep track of the locking. The port map daemon has to be running on the client side also. It's this port mapper that makes it possible to share and mount disk drives dynamically. An NFS file server can share any directory. Once the NFS daemons are configured, it's only necessary to list the file systems in the exports file. This system only exports one directory for remote mounting. The directory is named first, followed by the IP address of the hosts with which the directory is to be shared. The address is written in the form of a basic address and a mask. It's the same form that showed up in the routing table earlier. Now, this export line is sharing the home directory with any host that has an IP address beginning with 192.168.0. At the end of the line, in parentheses, are the permissions to be granted when the remote host mounts the file systems. RW indicates that both read and write permissions are granted. Also, if the remote user is a super user, he will retain his superpowers over this disk drive when it's mounted. Other options exist, but these two seem to be the most pertinent. We've looked at the fstab file before, but here it is again. Notice at the bottom of the list there are 4 NFS file systems. With them listed here in the file systems table, they will be automatically mounted when the system boots. It can happen that the mount fails when the system boots because the network could be down or the remote system could be down. You can mount everything mountable in the FS tab at any time by logging in as root and entering the mount command this way. The mount command with the A option reads the entries in the FS tab file and tries to mount anything that isn't already mounted. If you add a new entry to the FS tab, for example, you can use this mount command to execute that entry. Anyway, if you're going to set yourself up an NFS file share, you now have a good enough background in Linux networking to be able to follow the steps in the how-to and get it up and running. In the next lesson, I'm going to show you one way to hook up a modem. This lesson explains a way to connect a modem to your system and how to use that modem to connect to the Internet. You'll notice that I said a way, not the way. Remember that Unix was born at the telephone company. One of the first things it did was talk over a dial-up phone line. The original terminals were teletypes which operated over phone lines, and a lot of that legacy has been passed on to Linux. And the result is that there must be 20 ways to connect to a remote host, which is what a modem is all about. Anyway, I'm going to take you through a series of steps that not only will get your modem connected, but should also teach you something about the attitude Linux has toward modems in general. In the past, modem configuration was about baud rate speed matching and stop bits and other obscure configuration settings that you usually had to guess at until your modem finally matched up the one on the other end of the line and suddenly started working. Modems are much easier to work with these days. All you have to do is get your computer to talk to your modem, and it negotiates with the modem on the other end of the line about all the other details. There are, however, some rogue modems loose in the world that refuse to talk to Linux. These are known as Win modems, and they're built based on a secret handshake that's known only to MS Windows and the manufacturers of the Win modems. Unfortunately, Win modems are simply labeled modems, and the only difference is that they don't work. If you can't get your modem to respond to some of the simple commands that I'm going to show you, it probably means that you have the Win modem curse. External modems are a bit easier to work with because they connect to a serial port. Internal modems have two problems. Lots of them are Win modems, and they may need to have their IRQ and physical address ports set to one of the serial port values. At any rate, your first job is to get a modem connected to a serial port. To do that, you've got to find the device node that addresses the modem. Your device node that talks to the port may be named TTY or CUA or both, or it could be some other name. The ones shown here are the most common, but there's nothing magic about the names. This table lists a couple of common names for the device nodes for each of the two serial ports. You may know them by their DOS names as COM1 and COM2. The port addresses and IRQ numbers are set in the BIOS of the computer, and these shown are the standard numbers. If you wish, you can set them from the command line by using a utility named setSerial. A serial port is based on a hardware device known as a UART, U-A-R-T. A UART is a serial device. The utility named setSerial can be used to check for the presence of a UART by asking to report its current settings. You can check each device node that you suspect may be the port you're after, like this. You will either get a report like this from a UART, or you won't. If you do, you've got a serial port. As you can see on this system, the serial ports have more than one name. You may be more familiar with the DOS names for the ports, COM1 and COM2. The Linux numbers for these same two ports are 0 and 1 instead of 1 and 2. Anyway, on my system I plugged the modem in and found that I could talk to it through the port on CUA1. I suggest you use the LN command to make yourself a symbolic link to the port, like this. Now you can refer to your modem by that name. And if you decide to change the modem port later, all you have to do is change this link. Now the setSerial utility can also be used to set the IRQ and address, like this. If you decide to use set serial to configure your port, you'll need to be aware that the ports will be set back to their original settings whenever you boot the system, so you'll need to execute the set serial command every time you restart. You can do that by adding the set serial command line to the rc.local script in the rc.d directory. It's run at system startup every time. If you've gotten your modem connected and configured and you've created the symbolic link dev modem, then you can run minicom to talk to the modem. All you have to do is enter the name of the program like this. Don't let the warning about the configuration file bother you. You really don't need it. It's just to check out the modem. You might want to look into the man page for Minicom. It does a lot more than just what we're going to be doing with it here. If you don't get an OK prompt like this, then Minicom is not talking to the modem, and you need to go back and check your configurations and connections. That OK came from the modem itself. It's now waiting for a command. This command will instruct the modem to dial the number. You should hear the modem dial the number. Of course, unless this is the actual number of your ISP, nothing else will happen, so you can just break out of it with Control-C. Now you're still connected to the modem. If you want to see the Minicom commands, you type Control-A and then uppercase Z. As you can see from this list, Control-A followed by an uppercase Q should get you out of here. The next lesson continues with the modem. I'll show you how to set up automatic dialing to connect to the Internet. This lesson explains a way of getting a modem to connect to your Internet service provider and thus connect it to the Internet. As you may suspect by this time, there is a special protocol involved. In this case, the protocol is called PPP, which is an acronym for Point-to-Point Protocol. On most systems, the PPP daemon will have already been loaded and ready to go. You can check it with the lsmod command. The lsmod program lists all of the dynamically loadable modules, and the PPP daemon is loaded dynamically because it only needs to be running while you're actively connected to the Internet. The lsmod command will list it for you whether or not you're currently connected. If it's not installed, you'll need to get it from your Linux distribution CD and install it. Once it is installed, it may not be immediately usable because the dependencies for it may not be set properly. You can fix this setting in the dependencies for all loadable modules with a depmod command. Now this builds a complete cross-reference of dependencies, and that cross-reference is used when the kernel loads a module. You probably won't have to mess with any of this, but I thought I'd better tell you about it just in case. One more thing. The executables are in user sbin, and you need to change the execution permission on them. They're normally set for the root to use them, but if you want to give other users the ability to dial up, you'll need to give everyone execution permission. I allow everyone to dial up on this system. The configuration files for PPP are stored in the etc directory named PPP. Here's the way PPP works. You use another program to dial your Internet provider, and once a connection is made, that program turns the connection over to your PPP daemon. The daemon on this end then talks to the daemon on that end to authenticate the login and to agree on some basic terms for communications. There are a number of programs that you can use to do the actual dialing. They all work, but there's one that works better than any of the others. Add to that the fact that it's the easiest to set up and configure, and there's no need to go anywhere else. The name of the program is wvdial. You should already have it because it comes with most Linux distributions now, but if you don't, you can go to a Linux website that I gave you earlier to find the link to it from there. Anyway, once you have it installed, the configuration should take only a few minutes. Step 1 is to create a file named etcwvdial.conf. To get you started, wvdial provides a utility that will create the file for you. It's named wvdial.conf, and you run it like this. It searches for the modem. When it finds it, it will update the file. You can ignore that message about it not being able to read the file. That only means that the file did not already exist, but it created one and inserted the information it found into it. The file looks like this. Now step 2 is to edit this file. Remove the semicolons from in front of phone, username, and password, and insert your ISP's dial-up number and your login name and password. Step 3 is to set up the domain name servers. Right now, the name of the server won't help you. You must have the numeric IP address. Your ISP should have given you the address of your domain name server when you signed up, but if you didn't, I can show you how to temporarily fake it. Create the file resolve.conf to look like this. Now, if your ISP gave you the IP address of a name server, use it instead of the ones I have listed here. These are the addresses of 3 random name servers around the country. Whenever you're trying to resolve a name, such as locating a website or whatever, these locations are searched in turn for the IP address for that name. Once you get dialed up, I'll show you how to find out the IP addresses of your real name servers. Using the right ones will make things run a little bit faster for you. Now you can dial up the internet. This is the number I put in my wvdial.conf file. The host on the other end has started PPP negotiations, so wvdial has cranked up the PPP daemon to do the rest. The connection has been established. Now, this connection made by wvdial is persistent. That is, if the phone line is dropped or the ISP disconnects for some reason, wvdial will do what it can to get the connection back again. Try it. Turn off your modem, turn it back on again, and wvdial will reinitialize everything and dial up again. C will halt wvdial and break the connection. Now, you do have to log in as root to be able to dial up with wvdial, and you can run wvdial in the background so it won't tie up a terminal. You can do all of this using the scripting stuff that I showed you earlier. You can run wvdial in the background like this. Now, to get offline, you can use kill all. Kill all is a program that kills processes by name. Basically, it uses PS to look up the name and find the PID number of the process, and then issues kill to it. I just put this into a script named on and redirected the output to a file so I can check it later if there's a problem. You know how to do all of that. Now let me show you how to find out what the real name servers for your ISP are. The command named host is used to query for the name servers and their addresses. The V option requests a verbose output. Otherwise, you just get the names but not the addresses, and it's the addresses that you want. The type of query that we want to issue is for a name server, so its type is NS. This is the domain name of my ISP. And finally, we include the IP address of some name server out there on the internet. It doesn't matter which one. And there they are. The last 4 lines are the 4 name servers, names and addresses, and I need those addresses to add to my resolve.conf file. The dial-up configuration is now complete.